Okay, well, thank you very much for the presentation. And my name is Marcel Mosqueda. I am going to present today our work of a portable algebraic implementation for a reliable overnight industrial LESS. So I would like to start with the motivation of our work. So as we all know, the HPC continuous evolution towards a higher computational power, while continuing to optimizing the whole system energy consumption, has driven the development of different hybrid architectures. For example, mixing the CPUs with GPUs, as we all are familiar with, and taking advantage of the high parallel optimization of the GPUs, delivering higher power, a higher computational throughput, and a lower energy consumption. However, all this has driven, a new challenge, a small challenge, which is how can we achieve portable software for different architectures, also for different vendors? So our in-house CFD solver, as the previous presentation of Joseph was telling, is based on a truly conservative discretization methods using a set of algebra dominant kernels. This looks to answer this previous question because we look to only make portable these small kernels between the different architectures. However, we need to answer another question, which is these algebra-based implementation are not only portable, but also efficiently portable different CFD codes for different industrial applications. So to test this question, or all this question, we decided a numerical test. We are going to solve a turbulent channel flow using a conjugate gradient solver with a Jacobi preconditioner. We selected this solver because it's due to these low memory requirements, because for different applications, we can use different preconditioners. We are also going to use an explicit time integration scheme, applying a variable time step, and we are only focused to solve only the first time step using 800 iterations. We are going to solve this in two different systems, in a CPU system, also in a hybrid system, a GPU system, focused to get the strong algorithmic scaling. The CPU system are going to be solved in the Mare Nostrum supercomputer system located at the Barcelona center. The GPU, we are going to do this analysis in the Snellius GPU Iceland at Zorf in the Netherlands. So the first results that I'm showing here, it compares two different parallel paradigms using the MPI only versus the MPI plus OpenMP. It uses a baseline of one node of the Mare Nostrum 5 GPP supercomputer. We are focused to solve the largest problem that fits into the memory. This leads us to a mesh size of 58.8 million control volumes. As we can see here on the right side of the screen, this is the strong scalability test. We can see how the hybrid implementation, the MPI plus OpenMP, depicts as a super linear speedup, a super linear acceleration, super linear speedup. That is we assume that is due to the cache effect. This trend is sustained until of the 32-node solution, while the MPI-only solution follows the theoretical speedup up until the 8 nodes. Then the communications overhead started to take place, and apparently at the 32-node solution for both sides, we can see how the speedup started to slow down due to this communication. However, we wanted to stress our implementation to the largest problem side that we can achieve to solve. For that reason, we decided to set another baseline, in this case, starting at 16 nodes, and we're trying to scale up onto the maximum number of nodes that we can run this implementation in the Mare Nostrum 5 supercomputer. This is the results. As you can see, it shows similar results for the MPI plus OpenMP solution, when we can see the superlinear speedup for this result, while in the opposite side, the MPI-only solution, it started in the lower bound of the 70 to 100% efficiency region. This is because as we increase the number of CPUs that we are using to solve the problem, also we are increasing the number of halos, the number of MPI processors, the communication overhead must be higher than for the other process. On terms of the weak scalability, we are not showing here a perfect scalability or a flat plot, but it shows a smoother decrease of the performance until the 16-node solution, when we can achieve 90% of the efficiency. As you can see here as well, we are starting from the baseline of the 16 node, moving up to the solution for the 200 nodes. On regards of the GPU solution, here we set 4 MPI processes for each Snellius node. We define 1 MPU for each GPU core. And also we test, we use as a baseline only one node, which is composed for 4 GPU cards, 4 NVIDIA A100 GPU cards. And the goal here was also to solve the largest problem that can fit into the memory of the 4 cards, which is 160 gigabytes. On the right side of the screen is the strong scalability result. We can see here as it shows a steady speed up. However, it is not even within the 70 to 6 to 100 efficiency region. It is located within the 50 to 70 efficiency region up to the 8-node solution. For the 16-node solution, it still continues showing a speed up, but the result is approximately a 45% of the efficiency for the baseline, the current baseline that we are showing here. On regards of the weak scalability, it's possible to identify a steep decrease moving from the 1-node solution to the 2-node solution. We are assuming here this is due to the higher latency, due to the inter-node communication, because here we have another type of communication that takes place. But starting from this point onto the 16-node solution, we can see a smoother decrease that could reach until an 85% of efficiency for the 16-node solution. But in order to address some of the observation that we have made previously, and also to measure the implementation of our solver, we decided to perform a roofline analysis, something similar to the presentation for Joseph before. In order to do that, we defined 3 parameters, KPIs. The first one is the equivalent arithmetic intensity, we have an equivalent performance, and also a data throughput equivalent. The main idea here is just to create a weight average for each of one result, where the alpha sub k is the ratio between the number of operations of each one of these kernels to the total number of operations that have been performed. The first result shows the roofline for the CPU system. As we can see here, and also really similar to the result that Pep shows previously, the result as memory bandwidth, because we are limited by the memory wind. But however, it is optimized to deliver the 75% of the available performance that we have for the arithmetic intensity that we have. In order to measure what is the impact to the cache utilization, we decided to move into a hierarchical roofline when we have included also the shared cache memory bandwidth. And also we are plotting here the solution for the 16 nodes of the strong scalability for the hybrid paradigm. Here on the right side, we are showing a memory roofline. We can see here how the data throughput for the results that depicts the superlinear acceleration are using a higher bandwidth, more data movement that is over the RAM bandwidth, but is bounded also for the shared cache bandwidth here. Moving to the GPU performance, this is the roofline that we got for one node, for the solution for the one node, or the baseline. It shows similar results for the CPU. It's also a memory bound implementation, but in this case, the solution delivers a 95% of the available performance that we have for the current arithmetic intensity. We can see as the point is closer to the line. However, on the memory roofline, the plot here located on the right side of the screen, we can see a saturation for approximately at 85% of the bandwidth utilization for the data movement. We can see how all kernels are efficiently moving data per each calculation. We have a high usage of the memory channels. However, we decided also to put into the roofline the solution for the 16 nodes. As we can see here, this is the solution for the 16 node. For CPU, we were showing the strong scalability. Here we are comparing the weak scalability. In this case, we can see how points are almost overlapping each other. And also we have a reduction of 7% of the peak performance between these two solutions. But the difference that we can see here on the memory roofline is how the SPMV kernel reduce the data throughput. This could be done by a higher latency, or because we need to do more data movements in order to perform the same calculation that we did previously. Finally, we wanted to present what is the energy consumption, a comparison of the energy consumption for each system that that has been normalized by each time step, and also the number of control solvers that we have solved for all the weak scaling in both systems. We can see a reduction of around 74% between each system. For the lower energy consumption of the GPU, despite it requires a higher power, but all these gains we can attribute all these gains due to the high computational throughput that we have for each time step. So to wrap it up, in conclusion, we can see how our implementation, our design improves the portability into different HPC architectures. However, different efforts are needed in order to increase the arithmetic intensity to take advantage of the overall peak performance, as all of our solution due to the sparse algebra is highly memory bound. We can see how the CPU system exhibits a superior strong scalability compared to the GPU, especially with the parallel implementation, the MPI plus OpenMP paradigm, which deliver a higher speed up than the MPI only due to the higher cache utilization and also reduced communications overhead due to the reduced number of MPI processes required. Also, we can see how despite the higher power requirements of the GPU system, it leads to a lower energy consumption that is approximately a reduction of 74% in comparison with the GPU due to the gains for the higher throughput of the system. And finally, the weak scalability shows good performance in both systems, delivering a small drop in performance and computation times for as the problem continues increasing in size, which is mainly the goal for us to measure here. For future work, we would like to continue to perform large-scale urban simulation that trying to leverage the spatial regularities. The main goal of this is similar to the work that Pep previously showed. The focus is to increase arithmetic intensity using SPMM kernels instead of SPMB, but in this case is trying to take in advantages of the symmetries of the entire domain. But also we are trying to continue exploring strategies to increase the GPU computation for each data movement, especially for, you can see, for the SPMB kernels that is moving the data throughput down and also increasing the time to solve the problem as the problem increase. So thank you very much for your attention and open for any question that you will have.